Hi, my name is Dr. Robin, and today I'm going to be explaining how to write electron configurations if you don't want to use a diagram. As I said in the last video, electron configuration diagrams are pretty useful, but they do take up a lot of space, and sometimes we want to explain where electrons are in a more compact way. So that's what I'm going to show you in this video. Along the way, you'll get a bit more exposure to writing electron configurations. Let's start by looking at fluorine, which we did an electron configuration diagram for in the last video. This was what we came up with. So if you remember, we started off putting 2 electrons in the 1s orbital. We are going to represent that by writing 1s with a superscript of 2. Again, 1s is just the orbital we're talking about, and 2 is the number of electrons in that orbital. The next set of electrons went into the 2s orbital, and again, we put 2 there. So the next thing we're going to write is 2s superscript 2. And then finally, we had 5 electrons in the 2p orbital, and so we will write 2p superscript 5. So our written electron configuration for fluorine is 1s2, 2s2, 2p5. Let's try a different element. Here we have silicon, which is element 14. Assuming it's a neutral atom, we will have 14 electrons. The first 2 go in the 1s, the next 2 go in the 2s, and the next 6 go in the 2p. And that uses up our first 10 electrons. So we have 4 left, and 2 of those will go in the 3s, and then the last 2 will go in the 3p. Note that both of them have the same spin. So again, we're going to write this as 1s2, 2s2, 2p6, 3s2, 3p2. As a reminder, these superscripted numbers tell how many electrons are in each orbital, and so those superscripted numbers should add up to the total number of electrons in your atom. In this case, we have 2 plus 2 plus 6 plus 2 plus 2, which equals 14. This is a great way to double check your work. Let's do one last example. We are going to do strontium element number 38, which we will assume has 38 electrons. Again, we're going to put 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, and 6 in the 3p, which uses up 18 electrons. We still have 20 electrons left. Now, the 4s is the next lowest energy level, so we're going to put 2 electrons there. And then we can put electrons into the 3d, 5 with one spin, and then 5 with the opposite spin, so 10 total electrons in the 3d. We've now used 30 electrons and have 8 electrons left. The next lowest energy level is the 4p, and we know that we can put 6 electrons in there. That leaves us with 2 more electrons, and those are going to go in the next lowest energy level, which is the 5s. So now let's write an electron configuration for this. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. I should say that there is a bit of disagreement as to whether or not you keep all of the orbitals with the same end together. So some books say to put 3s2, 3p6, and 3d10 together, and then put 4s2 and 4p6 together, and then 5s2. And this is something that's open to debate. Both ways of doing things have different advantages. I personally prefer writing things in the order they are filled. So again, let's go do our check by looking at the superscripted numbers. We have 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2, and all that adds up to 38. So we're good. Again, we write out electron configurations to save space. When you get the hang of it, you can figure out electron configurations by writing them without drawing a diagram, and that saves time as well. Of course, there are some applications where diagrams are really necessary, like magnetism, but for the most part, you'll find that we will write configurations this way in the future. I hope this was helpful, and I look forward to seeing you again soon.